After the power normalization, the U00 function can be written in the following form. Clearly, you can see here a factor appears after the power normalization, and we can combine this term and the lambda here to express it like this. Okay, and now let's deal with this term. And the exponential term here can be expanded like this. As you can see, the complex term here has been expressed in this form shown here, and the exponential function, we have expanded the exponential function into these two. And after some arrangement, the above equation can be written in the following form. Okay, and this equation, you can see we will have the amplitude shown here, this term, and this term will correspond to the amplitude. And this term here will represent the phase. As you look at the amplitude function shown here, you will find that it is an Gaussian function. Okay, we have learned the Gaussian function in this form. So if you have function in this form, we call it a Gaussian function. So here is a Gaussian function. Besides, according to the Gaussian function I write here, you know that the Gaussian function, the curve of the Gaussian function can be plotted like this. And we define the radius of the Gaussian function is the position as the amplitude decay to the exponential minus 1 of the maxima. If here is 1, and if the amplitude decayed to exponential minus 1, the distance between this point to the center point, we call it the radius of the Gaussian beam. Or the radius of the Gaussian function. And from the expression shown here, you know that the distance, the radius of this Gaussian function will be the square root of a. And from this expression, compared to this one, you can see this exponential function is also a Gaussian function, a 2D Gaussian function. What will be the corresponding radius? The corresponding radius can be written as this one. We can obtain the radius of the Gaussian function by this one. So we can write it as this. Okay, so capital W square function gives us the square of the radius. Besides, you see here, this term. Compare with this one clearly, this term will give you the inverse of the radius of the Gaussian function. Okay? So the radius of the Gaussian function, we denote it as capital W function. And you can see, as we increase the value of z, the radius will be increased, but the W will be increased, but the inverse of the W will be reduced. What I'm saying is that as z increased, W of z will be also increased. As a result, the inverse of capital W will be reduced. This corresponds to the power conservation. As z is small, we have a Gaussian beam like this. The radius of the Gaussian beam is small, but the amplitude is high. But if z is large, the Gaussian beam will lose like this. Sorry, I should plot it like this. As z is large, the radius will be increased, but the amplitude, the height of the Gaussian beam will be reduced, okay, due to the power conservation. And from the phase turn here, you can clearly see that again we will have a curved phase front. Since we have a curved phase front, we would like to know what will be the radius of the curve. So we define a parameter r of z, which is the radius of curvature. And the r of z is just here. Okay, so this term I plotted in red line represents the radius of the curvature. And if z increased, you can see the radius of the curvature will also be increased, which means that this phase front will going to as a plane wave because the radius of the curvature is increased. Okay? Let us rewrite the U00 function. According to the beam radius and the curvature, the radius of the curvature, the U00 function can be written in the following form. In the above function, the capital W of Z represents the beam radius. Sometimes we also call it a beam size. Another important parameter is the inverse of R of Z, which is defined as Z over Z squared plus B squared. And this one is the phase front curvature. So, capital R of Z is the radius of curvature. Another one is tangent alpha. The alpha here, the alpha is defined as tangent alpha is Z over B. Okay, so this one is the solution of the Peirasio wave equation, and you can see it is a Gaussian function with the beam radius is capital W of Z, and this Gaussian function have curved phase front. The radius of the curvature is capital R of Z. From the above description, we can have some properties of the Gaussian beam. First, we like to find out the minima beam radius. From the expression here, you can see the minima beam radius will appear as Z is 0. Okay? What will be the value? So let's take Z is 0 into the capital W function. You will find out that the minima beam radius will be 2B over K. We call it W0. That is, if you plot the beam radius along the z-axis, you will find out that the Gaussian beam will have a minima radius at z is 0. Okay? And we find that the beam radius will be W0. And this position, we call it the waist of the Gaussian beam. The waist in Mandarin is the narrowest position of a human guy. Okay? And from this relationship, you can also say that the B can be expressed as K over 2 times the square of W0. Okay? Then, according to K is 2 pi over lambda, B can also be written as pi over lambda times W0 square. We call it confocal parameter of the Gaussian beam. And please keep in mind that the B must be a real value. The reason that B must be a real because we have defined that Z0 where the location of the singularity is minus JB. If B is a real, then the location of the singularity will appear in the imaginary axis. So if B is not a real, we will have singularity in the real axis. This is physically unreasonable. Since we have expressed the minima beam radius in terms of W0, so let's re-express the above two terms in terms of W0. So the square of the beam radius can written as the following equation. And the phase front curvature, that is the inverse of capital R, can also be written as this way. And the tangent phi is Z over B is lambda Z over pi W0 square. Okay? And in this slide, I will show you the properties of the beam radius capital W of Z as Z is changed. We have known that the beam radius capital W of Z can be written as this equation. So if you plot the capital W of Z, the beam radius, with respect to the Z, we have said that you will have a minima at Z is 0, right? And then, according to the expression here, you will see the capital W of Z will become large, will increase as we increase the value of Z. But you can see as Z goes to infinity. From the expression here, as Z goes to infinity, the beam radius capital W of Z will be approximated as square root of 2p over k times Z over B. Okay? Due to Z goes to infinity, compared to 1, this term will be very large, so we can 1 can be ignored. Okay? And this value will be re-expressed as this way. And then we can obtain it as lambda z over pi w0. And from this expression, you can see as z goes to infinity, the beam radius has a linear relationship with z. So this means that as z goes to infinity, the ray curve here will become a linear curve like this. And this position is the west as I have defined. Okay? And what will be this angle? According to the plot here, we know that the distance here is capital W of z, and the distance here is z. So you can easily to find it is easy for you to find out the angle theta. You can see tangent theta will be capital W of z over z. And as z goes to infinity, we take the approximation back into here. So tangent theta will be lambda over pi w0. Okay? And from the above equation, you will know that as z is 0, we will have a minima beam radius, which is w0. And as z goes to infinity, the beam radius will also goes to infinity. How about the phase front? We know that the radius, the phase front curvature, the inverse of Rz, according to the expression for the inverse of Rz shown here, you will see as z is 0, the inverse of Rz will become 0 too. So the phase front curvature will become 0. And as we increase z, the phase front curvature will become positive. But however, as z goes to infinity, as z goes to infinity, this term will be relatively very large compared to this term, and the phase front curvature will land in proportion to the inverse of z, which will become 0 again. Okay, let me say it again. The inverse of Rz is the phase front curvature, which can be written like this. And initially at z is 0, it is 0. And as we increase z, it will become positive. But if z goes to infinity, it will become 0 again. So if you want to plot the Gaussian beam along the z-axis, that is, if you want to plot the u00 function, you will see that it looks like this. The beam radius, like these two red curves, has a waist in the center in the z is 0. And the beam radius goes to infinity as we increase the value of z, or goes to infinity to the negative z direction. As for the phase front, initially the phase front is 0, the phase front curvature is 0. But as we increase the value of z, the phase front curvature will increase. But then they will go to 0 again due to it will become a plane wave. Okay, from 0 to positive and goes to 0 again. That is the variation of the phase front as the Gaussian beam propagates to the positive z direction. And you can also see the similar phenomenon along the negative z direction.